Welcome back. Last time, we just kind of scratched the surface of generalization error. Well, today, we're diving in deep. We're going to break down what this error is really made of and, more importantly, how we can actually measure it and get it under control. So, let's start with a situation that I'm pretty sure hits close to home for a lot of you. You build a model, right? It looks absolutely amazing during development, maybe hitting 99% accuracy on your training set, you're feeling great, but then you deploy it and it just bombs. It's almost useless. So what is going on here? Well, the answer isn't hiding in the data we've already seen. To solve this mystery, we have to look past our training set and focus on what really, truly matters: how our model performs on brand new data it has never, ever seen before. And that brings us to the absolute core concept for today, the expected generalization error. Now, you might hear people call it other things like expected test error, maybe even prediction error. But whatever you call it, this is the number we are always trying to make as small as possible in supervised learning. You see, the whole point of this isn't to build a model that's like a perfect historian, one that can just memorize the past. Nope. We're trying to build a fortune teller, something that can accurately predict what's coming next. The real goal is to create a function that works reliably on data it's never encountered. Okay, so that leads to a huge question, right? If we can't actually see future data, how in the world do we get a decent estimate of this generalization error? We've got two main strategies for this. First, there's the validation set approach. It's simple. You just split your data once. It's fast, but your estimate can be all over the place, kind of unstable, depending on how that one split went. For a much more solid result, we turn to cross-validation. It's way more robust and gives us an estimate we can actually trust. And this lays out the most popular way to do it, which is k-fold cross-validation. The idea is so simple but so powerful. Instead of just one split, you do several. You train the model over and over, each time using a different piece of the data for training and testing it on the little chunk you held back. Then you just average all those results together. What you get is a much more accurate picture of how your model will actually perform out in the wild. It's just a brilliant way to squeeze every bit of value out of your data. All right, so now we've got a solid way to estimate our generalization error. So let's actually put that error under a microscope. What's it made of? What are its different parts? So it turns out, when we're using squared error as our loss function, something really cool happens mathematically. The total expected error neatly decomposes into exactly three components, something called irreducible error, the squared bias, and the variance. This table kind of gives us the whole map. We've got error that comes from just pure random noise. We've got error because our model is too simple. And we have error because our model is way too complicated. Getting a good feel for these three sources, that's the real secret to building great models. So first up is the irreducible error. You can think of this as the built-in randomness or noise in the system you're trying to model. It's the stuff your features just can't explain. And no matter how amazing your model is, you can never get rid of this error. It sets a hard floor on how well you can possibly do. Okay, then we have the two types of error we can actually do something about. On one hand, there's bias. This is the error you get from your model making the wrong assumptions. Basically, it's too simple and it's missing the real patterns. We call that underfitting. Then on the other hand, you have variance. This is the error you get when your model is too sensitive to the training data. It's so complex, it starts modeling the random noise instead of the underlying signal. And that is classic overfitting. So what this all means is that getting the lowest possible error isn't as simple as just trying to crush bias or just trying to crush variance. No, you have to do this delicate balancing act between the two. Think about a really simple model, like trying to fit a straight line to data that's clearly curvy. It's going to be wrong a lot of the time, so its bias is high. But if you get a slightly different set of data points, the line isn't going to change very much, so its variance is low. That's underfitting in a nutshell. Now, flip that around. Imagine an incredibly complex model, a super wiggly line that perfectly hits every single one of your training data points. For that data, its bias is basically zero. But if you were to change just one of those data points, the whole curve might swing wildly. That's high variance, and it's the textbook sign of overfitting. And this right here is the core job of a data scientist. Our task is to find that sweet spot. We have to pick a model with just the right level of complexity, not too simple, not too complicated, that hits that perfect balance and gives us the lowest total error, So we've gone through the theory behind mean squared error, we've broken it down. But what about the metrics we actually use day to day? How does all this apply in the real world? At the end of the day, truly understanding this bias variance trade off is what separates someone who can just run a model from someone who can actually engineer a robust, reliable, predictive solution that works in the real world. And that kind of leaves us with one last question to think about. This beautiful breakdown works perfectly for mean squared error. But what happens when we take the square root to get RMSE, a metric a lot of us prefer because it's easier to interpret? Does this whole framework still apply? Join us next time to find out as we dive into the decomposition of RMSE. See you then.